Okay, in this video we will make some practice with the roots of complex number z. Roots of a complex number z. Remember that in the last time we found this fundamental formula that if we want to find the nth root of z, this is given by rho raised to 1 over n times e to j theta over n plus k times 2 pi over n, where k is takes value from 0, 1, 2 up to n minus 1. Okay, let's apply this formula to some numeric example. For example, let us consider the fourth root of minus 2 square root of 3 j. Okay, so we know that the first step here is to transform this complex number into its exponential form. So the first step is to evaluate rho the modulus, which is the square root of minus 2 squared plus minus 2 square root of 3 squared, and this is the square root of 4 plus 4 times 3, and this is 4 plus 12. This is the square root of 16, which is 4. While the argument theta, in this case the arctangent of minus 2 square root of 3 over minus 2, and we have to add pi because the real part of z is less than 0. And minus 2 and minus 2, they cancel each other, so the arctangent of the square root of 3 is pi over 3 plus pi, so we got here 4 pi over 3. Okay, right. So now we can consider this as the fourth root of this number written in exponential form becomes 4 times e to j 4 pi over 3. But if we apply this formula, keep in mind, this is the fundamental formula that we have found last time, which allows us to find the nth root of a complex number. If we apply this, what I found is that this is equal to the fourth root of 4 times e to j. Theta in this case is 4 pi over 3, 1 over 4 times 1 over 4, because this is n is 4, plus k times 2 pi over 4. And this expression can be easily simplified as the modulus becomes the square root of 2, while this is e to j. 4 and 4, they cancel each other, so this is going to be pi over 3 plus k times 2 pi over 2. So let us consider the values. The values of k to be considered are 0, 1, 2, and 3, because n is 4, so 3 is the last value of k that we have to consider. Well, for example, let's start with the value k equals 0. Okay, if we consider k equal to 0, the root, I will denote the first root, the root corresponding to the value k equals 0 as z sub 0. And this is the square root of 2 e to j pi over 3, because this term does not exist. If we consider k equals 1, z sub 1 is the square root of 2 times e to j. What I got here is pi over 3 plus pi over 2. But this is square root of 2ej. Well, this is 5 pi over 6. While for k equals 2, what I got here is z sub 2 equals square root of 2a to j pi over 3 plus 2 times pi over 2. And this is the square root of 2 a raised to j. What do we have here is simply, well, I have here pi over 3. Well, the common denominator is going to be 6, so we have here 2 pi plus 3 by 2 is 6 pi. So exactly, this is going to be square root of 2 e raised to j section 2 is 8 pi over 6. While the last value for k equals 3, I got z sub 3, which is the square root of 2 e to j pi over 3 plus 3 times pi over 2. And in this case, we get square root of 2 e raised to j. What do we have here is, of course, the denominator is always 6. So we get 2 pi here plus 6 divided by 2 is 3 by 3, 9 pi. So I got exactly e raised to j 11 pi over 6. Now, if we want to find the position of this roots, we know that all these roots are located on a circle with a radius that is the square root of 2, of course. The z sub 0 is positioned at pi over 3 radians. So pi over 3 is roughly here. So this is the position of z sub 0. While z sub 1 is positioned at 5 pi over 6. Okay, this is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. This is 5 pi over 6. So this is z sub 1. While z sub 2 is located at 8 pi over 6. Okay, this is 6. This is 7 pi over 6. I'm sorry, it's not a great line. This is 7 pi over 6. This is 8 pi over 6. So this is z sub 2. And the last one, z sub 3, has as argument 11 pi over 6. Of course, this is 9. This is 10. And this is 11 pi over 6. So this is z sub 3. As we can easily see, these 4 roots are located at equal distance, are equally distributed over the circle. They have equal distance, angular distance, one from each other. And it is very interesting to see that they are vertices of a square inscribed inside the circle. And this is exactly why the reason for this is that roots are equally distributed over the circle, because they differ from this multiple of pi over 2. This is a general rule, as we will see also in the next example. Whenever we have to evaluate the nth root of a number z, we will get n values, and all these values are vertices of an anagon which is inscribed inside the circle. Let's see, for example, let's see another example in which we will check it out that this is true. For example, let's try to evaluate the 5th root of -1. Okay, the first step, as we all know, is find the modulus, but the modulus here is very simple, is 1, while the argument theta is the arctangent of 0 over minus 1, and we have to add pi in this case. Okay, so the arctangent of 0 over minus 1, of course, is 0, so this is 0 plus pi, and this is pi. And this is easy to see, yes, because in fact, as we draw this point, this complex number minus 1 is exactly a complex number with an argument which is exactly pi. Okay, now we have found rho theta, so this root can be expressed as the fifth root of 1 times e to j pi. If we apply the well-known formula now, what I got is 1 over raised to 1 over 5 e j theta is pi over 5 plus k times 2 pi over 5. So this has to be evaluated for the values of k ranging from 0, 1, 2, 3, 4. So let's first evaluate z sub 0. Well, z sub 0 is simply given by 1 raised to 1 over 5 is 1. I would not rewrite this modulus. I would assume that 1, of course, is in front of each expression. So this is e raised to j pi over 5 because k is 0. Z sub 1 is going to be e raised to j pi over 5 plus 1 times 2 pi over 5, and this of course is e raised to j 3 pi over 5. Z sub 2 is going to be e raised to j pi over 5 plus 2 times 2 pi over 5, and this is e raised to well, this is 5, sorry, this is 5. Okay, so here I got exactly j pi, yes, because pi plus 4 is 5 pi over 5, which is pi. Z sub 3 is e raised to j pi over 5 plus 3 times 2 pi over 5, which is e raised to j. What I got here is 3 by 2 is 6 and 1 7 pi over 5, 7 pi over 5. While the last one, z sub 4, is e raised to j pi over 5 plus 4 times 2 pi over 5, and this is e raised to j. What we have here is 9 pi over 5. So if we want now to see where these roots are located on a complex plane, well, we soon know that all roots are located on a circumference with a radius of 1. The first root is located as pi over 5. Pi over 5 is roughly here, okay? This is pi over 5. While the z sub 1 is 3 pi over 5 is some place that is here. The third, which is z sub 2, is located at pi, so in this place, so this is z sub 0, this is z sub 1, this is z sub 2, and of course the z sub 3 is located at 7 pi over 5, but this is pi over 5, this is 3 pi over 5, and this is 7 pi over 5 has to be located in some place here, 7 pi over 3, this is z sub 3, while the last one, z sub 4, is located in this place, z sub 4. And what comes out of this? Well, comes out that we have the roots that are vertices of a pentagon inscribed in a circumference with a radius of 1. And this confirms what we have said before. In this case, we had to evaluate the fifth roots of this number -1, and we found out we have found 5 roots which are positioned on a circumference, on a circle with the radius 1 at equal distance, and that are vertices of the pentagon. Okay, that's all for now. We had a look at how the exponential form is convenient to evaluate the n root of a complex number. Next time we will take a look at some properties of the modulus and argument of a complex number. Thank you for now.